So in this video, we're going to continue our understanding vector algebra, and I'll go through examples so we can actually create vector equations. So imagine the following. Somebody gives you an abstract representation of saying that 3i plus 4j. But remember what this means. This means literally from our last videos, right? You should have an understanding. This means, so if I and j, I was a direction for east and j was for direction north, this is 3 meters east and 4 meters north. So this is 3i plus 4j. And somebody defines b vector is equal to 2i minus 3j, and c vector is equal to something, I don't know, but I'm told that the following is true, that 2a minus 3b plus c is equal to 0. This is called a vector equation. So our problem is, can we solve this vector for c? So let's go through the calculation, okay? So when somebody says 0, this is a notational convenience. Nobody wants to write 0i and plus 0j, but it is. When somebody writes 0, this is actually an abbreviation for saying this is, you didn't travel east and you didn't travel north. Where are you? You're at the origin. So this symbol that we write over here is an abbreviation for this thing. Not traveling east, nothing traveling east, nothing traveling north. So you're at the origin. So it's an abbreviation. So the question is, how can I solve for c? Well, let's plug it in. Let's plug in that 2 times 3i plus 4j minus, so I'll put this as a plus minus 3, times b, which is 2i minus 3j plus c vector. I don't know what that is yet, but I'll put this equal to 0. So we calculate. We know that when we do scalar multiplication, we multiply the scalar number, the value, into the vectors. So this is really twice of 3 meters east and 4 meters north is really 6 meters east, which is 2 times 3. This is called the distribution law. You're distributing the 3 over the other values. 1 sec, 3. And I plus 2 times 4 and j plus negative 3 times 2i minus 3 is a plus 3 times j plus c vector is equal to 0. So I'm going to rearrange these terms and move the i's together. So I'm moving this term and this term together. So now I'm going to say it's 2 times 3 minus 3 times 2, and the whole thing is I. So I've rearranged them and pulled out the I. And we can do that because if you're traveling in the east direction, it doesn't really affect your northerly direction. And actually, well, so I'm putting the i's together and I'm putting the j's together. So here's our j vector. And sometimes, remember, this is just a notational convenience that's saying this number represents the amount of northness. Whether you put the north first or last, it's a placeholder. So some people, and like I sometimes do that, I like putting j sometimes in front and say this is really 2 times 4 north, 8 meters, and 3 times 3 j, which is this term. So I'll put a box around it so you know that these two terms are coming together. So here's our box term, and here is our oval terms for these two terms. So we can now get, let's keep this vector equation going. C equal to c. And then, so this is now 6 minus 6, which is 0. Whoops, I think, yeah, actually it is 0. I did select 2i, yeah, I guess I did. That's 0. So this is 0i plus 8 minus 9 is minus 1, and I'll put the j now at the back. The order doesn't matter because we know that this number is how much north you've traveled, which really means you've traveled 1 meter south. So plus a c vector is equal to 0. Now, if you remember your basic algebra, you know that when you move things in algebra equations, right, you move things around. We can actually prove this step by step, but I'm just going to go through the steps and hopefully you're understanding this. So I'm going to move the minus 1j and I to the other side. In fact, I'm not even going to write I because there is no I. We haven't even traveled east or west. So I'll move this term to the other side and write c is equal to minus of minus 1j, which is equal to c vector is equal to 1j. So what is c? C vector is 1 meter north. If you remember, if I select I to be the direction east and j to be the direction north. So this is called a vector equation, and we are solving a vector equation. So let me give another example so we can actually feel comfortable with these vectors, right? So let me erase everything. So thus far, you probably learned acceleration and velocity and displacement. And so let's do velocity. So imagine the following problem and let's convert this into a physics problem. A car travels at 3 meters per second. Actually, let's make it, yeah, travels 3 meters. 3 meters the east. And then travels 4 meters north in a total of 10 seconds. So actually maybe 3 meters is kind of small and 4 meters if you're in a car, but well, it could be a small children's car. So anyway, but it traveled 3 meters to the east in the beginning and then travels 4 meters in a total of 10 seconds. Find the average velocity. So you have to remember, so the car, right, is originally at a point, then it travels this way. How do I signify that it went to east, 3 meters east? It would travel 3 meters east, and then it traveled 4 meters north, east, north. But nobody wants to write this. We want to write it a better way and say, how do I say it traveled 3 meters east and 4 meters north in 10 seconds? Well, 3 meters east, that velocity, or the displacement, I should write d as displacement. The displacement vector is you travel 3 meters east, I'll write it out in words, and 4 meters north. But in our abbreviated way of doing vector notation, right, this really is 3i plus 4j. We know that now we spent a little time, and this is kind of looking back, and hopefully you feel comfortable with this. So velocity vector, right, is the displacement vector divisible by time. So in this case, it happens to be abbreviated as 3i plus 4j all over 10 seconds. And I'm assuming SI units. So this is now 0.3i plus 0.4j. And in units, right, we'd write this in standard units as meters per second, because I'm going to be using, in all my notes, I'll always be using standard units. So if I'm looking at distances, I'll always say this is 3 meters east and 4 meters north. So our velocity vector, right, the average velocity vector is 0.3i plus 0.4j. Notice how simple and mathematical everything is. We have simple statements. Instead of writing this, we've written 3i plus 4j. That's my displacement. I travel from some point. I don't want to write 3 meters east and 4 meters north. I just write 3i plus 4j. And that's in units of meters. And divided by time, distance over time is the velocity vector. Let's do another example. Let's do acceleration. Imagine a car rounds a corner. So here's our car, and it's traveling at 10 meters per second. And it's traveling this way, and then it travels this way. So I'm going to assume that it's traveling with a velocity, initial velocity, and no vector. I'm just putting 10 meters per second. It's traveling that way, 10 meters per second, and then it's traveling at final velocity is 10 meters per second down. Okay? And it does this. Let's make it really easy. Let's say it's in 10 seconds also, the time. So we're assuming that, and the question is, find the acceleration. Acceleration. So this is not a vector, it's just a number that says the velocity magnitude is 10 meters per second. But how do we write that as a vector? So what is the initial velocity? Well, if it's going 10 meters per second that way, and if we specify that this direction east is the symbol I, and north is the symbol J, and down is minus J, so VI, the initial vector, is 10 meters per second east. That's the direction it's traveling. What is the final velocity? V final is, well, it's going down, and my way of specifying down is minus J. If you remember, east is I, west is minus I, and north is J, down is minus J. So this is now minus 10 meters per second. And so what is my velocity vector? The final velocity. What is acceleration defined to be? Acceleration is V final minus V initial over time. In this case, it happens to be minus 10J and then minus 10I, all divisible by 10 seconds. And if you divide 10 into here, you get minus J and minus 1I. And this is standard units, so acceleration should be in units of meters per second squared. So if you have to draw this out in a vector diagram, right? And you'll notice the following, that this direction minus J, so I'll imagine this is an acceleration graph, right? And I'm actually drawing the vector for minus J minus I. So this is saying minus 1 east, this way, this point, minus 1 south, it's this, that vector. This is 1 and this minus 1. And this is minus 1 and 0 and 1 and 2 and so on. So this is I and this is J. So the acceleration vector. And if you're wondering, right, would we actually see this? If you do it graphically, right, let's draw it graphically just to make sure that it's pointing the right direction, to make sure that your understanding of using vectors and symbols, right, this vector notation makes sense. So let me erase this. Graphically, right, what does this mean? So here is V final minus V initial, and I won't multiply by 10, it's 1 over time, right, which is 1 over 10 seconds. So V final, what is V final? V final, and let me just do this, V final minus V initial. That is V final plus the negative of V initial, which is graphically written as, so we have to do tip to tail, right? So here's our vector going down. Here is V final. This vector, I moved it down to over here. Hopefully I'm drawing it properly. And V initial happens to be a vector minus V, so minus V is going in the opposite direction. This is minus V. This is V final. And then we draw tip to tail, which is a vector, and which kind of makes sense, exactly the same direction as I expected. Minus, so where's this direction? It's going in the negative, it's going to the west, and it's going south, or negative east and negative south. Sorry, negative north. So basically our understanding, right, is that instead of doing graphically, we're doing it algebraically. So just know that they are the same thing. So this is an example of adding and subtracting vectors. Let's do another example. Let's imagine the following scenario. an object is located at 3 meters east and 4 meters, let's say, north. It accelerates. It has initial velocity of 0. It accelerates to the west at 4 meters per second squared for 10 seconds. A nice round number, so I don't have to think. So it's traveled to the west at 4 meters, 10 seconds. 3 meters and 4 meters north. So I'm saying this object relative to some origin, some reference point. And then find the position of, actually find the final position. Okay, so it should be final position of the object. If you remember right, there was 2 vector equations for uniform acceleration, and the second one, right, was a displacement. So if you had to memorize this, that the displacement vector, right, was given by the initial position vector plus the initial velocity times time, this is a vector equation, times 1/2 a times t squared. So the question is, what is the initial displacement? Where is the object in our frame of reference? Well, the object is located 3 meters east and 4 meters north. So in some arbitrary coordinate system, 1, 2, 3, and we don't even have to draw this, but it's located 3 meters east, 4 meters north, up here somewhere. Well, how do you write that in vector notation? Well, you don't want to write this in English, so we want to use the contraction. 3 meters east and 4 meters north. 4i, 3i plus 4j. What is the initial velocity? It's not moving. It has initial velocity, so that is 0, 0. Or if you want, if you feel more comfortable, you can say it's 0i plus 0j, but 0 is fine. And then 1/2, what's the acceleration? If we look carefully here, it says it accelerates to the west at 4 meters per second squared. That's at. So, but 4 meters per second squared west is really minus 4 meters per second squared east. But remember, in standard units, and this is squared, I usually don't put down the units except so as if I'm using standard units in SI. So whenever I see an acceleration, I'll automatically say it's in meters per second squared. So we can now write the vector equation. So this is the final position is going to be equal to our initial position, 3i plus 4j plus 0, actually I'll just say it's 0, times 10 seconds plus 1/2 times acceleration, which is minus 4i times 10 squared. And I'm going to draw a line there so you don't confuse anything. So this is just 0, and there is no 0i plus 0j, so that's all 0. So this is now 3i plus 4j plus, then minus 4, that's negative 2. Negative 2 times 10. 10 squared is 100. 100 times 2 is 200. So this is minus 200 I vector. So 400 divided by 2 is minus 200. So add up the positions of the i's. The i's are next to each other. Sorry, this is I. So this is now 200 minus 3, or minus 197i plus 4j. So where is the final position? It is negative 197 meters east and 4 meters north. Or if you want, it's 197 meters west and 4 meters north. So this is an example of a vector equation. And you have to feel comfortable with vectors, because if you do, right, most of physics, right, where we use coordinate systems, is pretty straightforward. So it's an important aspect of describing nature if we can define this algebra so we can actually say simple things. For example, Newton's laws, right, can be written very succinctly as, actually Newton's laws are actually 3 laws, but let's talk some other time. It's actually law number 2 and law number 3 that's really important. Law number 1 is a special case of law number 2. But anyway, let's talk about that in the next video, another video.